Divide and conquer algorithms, or recursive algorithms, is one of the first algorithmic tools that many of you may have learned. For example, binary search or merge search. To see the power of divide and conquer, we'll look at a fundamental problem. Given n numbers, we'd like to find the median element. The numbers are unsorted, so they are in arbitrary order. Can we find the median without first sorting the list? We'll look at a really ingenious divide and conquer algorithm to do just that. This is the problem of finding the median. The input to the problem are n numbers, and these are in arbitrary order, so we assume the list is unsorted. And the input is given to us as this one-dimensional array, capital A. Our goal is to find the median of A. This is the middle element. When n is even, it's not exactly clear what we mean by the median. So for concreteness, let's define the median as the n over second ceiling, smallest element of A. So when n is odd, so n equals 2 times L plus 1 for some integer L, then in this case, the median is the L plus first, smallest. And there are exactly L, which are at most this median element, and there's at least L, which are least this median element. It'll be useful for us to solve a more general problem. Instead of finding the median element, we want to find the k smallest, where k is an input given to us. More specifically, we're going to look at the following problem. We're given an unsorted list A, just as before, and we're also given an integer k, where k is between 1 and n. And our goal is to find the k smallest of A. So if we set k equal to n over 2, then that'll be the median. Now if A happens to be sorted, then it's easy to find the k smallest. We just output the kth element of the sorted list. So that gives us a very trivial algorithm for solving this problem. Given an arbitrary A, we simply sort A, and then we output the kth element of this sorted list. How long does this algorithm take? Well, merge sort, or several other algorithms, take order n log n time to sort A. So the total runtime of this algorithm will be order n log n. Now, is it possible to find the k smallest without first sorting A? That's what we're going to do now. And in fact, we'll find the k smallest in order n time instead of order n log n time. What we're going to do now is this very clever divide and conquer algorithm for finding the k smallest in order n time. This algorithm is due to Blum, Floyd, Pratt, Rivest, and Tarjan from 1973. The story is that they figured it out over lunch. Once you see the algorithm, and it's quite clever, it'll be quite impressive that they just figured this out just over one lunchtime. Now we're going to use divide and conquer to solve this kth smallest problem. And our algorithm, the basic approach, is going to be quite reminiscent of the Quicksort algorithm. Let me remind you about the Quicksort algorithm, and then we'll see the modifications for our approach. So we're looking at Quicksort for sorting this unsorted list A. The first step in the Quicksort algorithm is to choose a pivot, P. Then we partition the array A into 3 buckets based on their relation to the pivot, P. One bucket is for those elements strictly smaller than P, those equal to P, and those strictly bigger than P. We do one scan through the array A, and we put each element into one of these 3 buckets. Then we recursively run Quicksort on the small elements and the big elements. We take the output, and our final output is the sorted list of the small elements, followed by the equal elements, followed by the big elements. Now recall, the whole challenge in Quicksort is how to choose a good pivot. If we choose a terrible pivot, such as the smallest element or the largest element, then one of these 2 lists is going to be of size n minus 1. It's just going to go down by 1 element. And then the running time of our algorithm is going to be order n squared. So what's a good pivot for Quicksort? It's the median, or something close to the median. For our problem, we're going to have the same challenge, how to choose a good pivot. That's going to be the main task. But Quicksort ideally runs in order n log n time. We're aiming for an order n time algorithm. The key is that we don't have to recursively consider both A less than P and A bigger than P. We only have to recursively search in one of these 2 lists. Let's look at a specific example to see exactly what I mean for this third step. Let's look at the following example with an array of n numbers. And let's choose a specific pivot. Let's say the pivot is number 11. So we make these 3 buckets, those less than P, those equal to P, and those bigger than P. And we're going to take a scan through the array, and we're going to put each of these elements in one of these 3 buckets. 5 is smaller than the pivot. 2 is smaller than the pivot, and so on. 11 happens to appear twice, so it appears twice in this equal list. And these are the final buckets. Now what is the k we're searching for? Depending on the k we're searching for, the k smallest will be in one of these three lists, and we can figure out where it resides based on how large these lists are in comparison to k. The smallest list is of size 4, so if k is at most 4, then we know the k smallest is in this list. So in this case, what we can do is we can recursively search for the k smallest in this list, and we can discard these two other lists. Now if k is 5 or 6, then what do we know? Then we know the k smallest is in this list, and then, therefore, it's equal to 11. So we don't need to recurse at all. We can just output 11. Finally, if k is bigger than 6, then what do we know? We know that the k smallest is in this list. So we don't search for the k smallest in this list because we discarded 6 elements from these lists. So we're going to search for the k minus 6 smallest in this list, a greater than p. Now the key is that we're always recursing on at most one list, either the small list or the big list, or in the middle case, we don't even have to recurse at all. Whereas Quicksort has to recursively sort these two lists, less than p and bigger than p. In this case, we only have to recursively search in one of the two lists. Now let's go ahead and detail this for the general case, and let's write the pseudocode to make sure it's all clear. Now we're aiming for an order n running time, and we're trying to use divide and conquer. So let's look at the recurrences which yield an order n solution, and then this will give us some idea of the algorithm basic approach. Take a look at this recurrence. What does this recurrence solve to? T of n equals T of n over 2 plus order n. This recurrence solves to order n. How can we achieve a running time like this from the basic approach that we outlined on the previous slide? We have one subproblem which is of size at most n over 2. Well, in our previous approach, we either recurse on a less than p or a bigger than p. In order to achieve that the subproblem is of size at most n over 2, we need that the pivot p is the median. If the pivot is the median of the unsorted list, then we know that a less than p is at most n over 2, and a bigger than p is of size at most n over 2. And therefore, the running time of our algorithm will be exactly this, which solves to order n. Now the problem is that the whole problem that we're trying to solve originally was to try to find the median of this list. So if you give us a solution, then I can run for order n time and I can find the solution again. That's the punchline so far. But what if I don't actually have the median exactly? What if I have an approximate, a reasonable guess of the median? So suppose p is an approximate median. It's fairly close to the median, but it's not exactly the median. Let's just do a thought process. Let me look at this sorted array A. So I'm not actually sorting A, but I'm just thinking about it, this array A as being sorted. Then the median is lying right here in the middle. And here I have the smallest element, here I have the largest element. Let me look at the n over 4 smallest, and let me look at the 3n over 4 smallest. Suppose instead of giving you the median, I just give you something which is guaranteed to lie within this band. So it's at least the n over 4 smallest, and it's at most the 3n over 4 smallest. So it's not lying in either of these extremes, it's lying in this middle band. Suppose I can find a pivot which satisfies this. So it's going to lie in this band. What does that imply about the running time of my algorithm? How large are these subproblems going to be in the worst case? Well, in the worst case, maybe it lies right here. It's the 3n over 4 smallest. And then a less than p is going to be of size 3n over 4. Similarly, if it's n over 4 smallest, then a bigger than p is going to be of size 3n over 4. And in general, I know that the size of the subproblem is going to be at most 3n over 4. So my recurrence is going to satisfy this relation. Now the question is, what does this recurrence solve to? Turns out it still solves to order n. And in fact, I can relax it even more. I don't even need 3/4 here. I can look at the n over 100 smallest here, and then 0.99 n smallest over here. I just have to chop off a constant fraction on both sides. So what is my recurrence going to satisfy in this case, where it lies in this bigger bandit? So my pivot is at least the n over 100th smallest, and is at most the 99 over 100th smallest. In this case, the size of my subproblem is at most 0.99 n. So my recurrence satisfies this relation. What does this solve to? This also solves to order n. The key is, I need a constant here which is strictly less than 1. So I'm always chopping off a constant fraction of the nodes. Now we're going to define a good pivot as a pivot which lies in this middle band, between n over 4 and 3n over 4 smallest. That's going to give us this recurrence. But it's going to be important for our algorithm, actually, to remember this recurrence. We have some extra slack. So we're going to aim for a pivot which satisfies this relation. But there was going to be some extra slack because I'm allowed to have any constant less than 1 here. And I'm going to have to utilize that extra slack in order to find the pivot, which is a good pivot. So in the end, our running time is going to satisfy a relation similar to this bottom recurrence. But our definition of what is a good pivot is lying in this middle band between n over 4 and 3n over 4th. Now our aim is to try to find a good pivot in order n time. And we want to do this in worst case order n time. What we just saw is an algorithm which finds it in order n expected time. Now if we can successfully find a good pivot in order n time, then the running time of our algorithm will satisfy the following relation. T of n is at most t of 3/4 n because it's a good pivot. So the subproblem will be of size at most 3/4 the original size, plus order n to find the good pivot, and order n to partition A into the 3 sets. Now this recurrence solves to order n. So the overall running time of our algorithm will be order n. Now we have a bit of slack in this recurrence. In particular, recall that instead of having 0.75 n over here, we could have had 0.99 n. We just need some constant less than 1. What we're going to do is we're going to use this extra slack as extra time to help us find a good pivot. So now we're going to spend, instead of just order n time to find a good pivot, we're going to spend order n time plus t of 0.2n. So we're going to design an algorithm with the following running time. T of n is at most t of 3/4 n. This is for the subproblem, once we find a good pivot, plus t of n over 5 plus order n. This t of n over 5 plus order n is going to be the time it's going to take us to find a good pivot. Now the key fact is that 3/4 plus 1/5 equals 0.95. It's strictly less than 1. So this recurrence solves to order n. So if we can find a good pivot in this amount of time, t of n over 5 plus order n, then we successfully have an order n time algorithm to find the median. Now what exactly are we going to utilize this t of n over 5 in order to find a good pivot? How are we going to utilize it? Well, we're going to choose a subset of A, which is of size n over 5, and then we're going to recursively run our median algorithm on this subset S. And we're going to set P, the pivot, to be the median of this subset S. The time it's going to take us to find the median of this subset S is going to be t of n over 5, since the subset S is of size n over 5. The question is, how do we choose this subset S? We need to choose this subset S so that it's a good representative sample of this entire array A. Now let's detail the pseudocode for our linear time median algorithm. The input to the algorithm is an unsorted array A of size n and an integer k, where the integer k lies between 1 and little n. And the output of the algorithm is the kth smallest element of the array A. The first thing we need to do is find a good pivot. To do that, we break A into n over 5 groups of 5 elements each. Now to be precise, we should say the ceiling of n over 5 groups, because little n might not be a multiple of 5. But let's ignore floors and ceilings in this pseudocode. Let's denote these n over 5 groups as G1, G2, up to Gn over 5. Now how exactly do we break A into these n over 5 groups? Well, we can do it in any arbitrary way we like. The easiest way to do it is to take the first 5 elements of A and put those into group 1, take the next 5 elements of A and put those in group G2, and so on. Now we have to choose one representative from each of these groups. Here's a for loop to go over the n over 5 groups. For the ith group, group Gi, we want to find the median. To do that, we first sort this group. There's only 5 elements, so we can take any algorithm we like to sort it. And then we take the median of these 5 elements. And let's let Mi denote the median of group Gi. Now we want to look at these n over 5 medians which we found in step 2. Let's let capital S denote this set of n over 5 medians. Next, we want to find the median of this set S. This will be our pivot P. How do we find this pivot P? How do we find the median of this set? Well, we recursively call this same algorithm fast select on this subset S. Now S has n over 5 elements. We want to find its median. Therefore, we look for k equal to n over 10. The n over 10th smallest element of S is the median of this set S. And we store that in element P. Now we use P as our pivot. We partition the original set A into 3 sets. Those elements less than pivot P, those equal to the pivot P, and those bigger than the pivot P. This requires just one scan over the set A. Now we can use the quick select approach from before. Based on the sizes of these three sets, we either recursively search in the small set, the big set, or we simply output P. In particular, if the size of the small set is at least as large as K, then we know that the K smallest lies in this small set. So we recursively run this same fast select algorithm on the small set, looking for the K smallest. Now if K is big enough, in particular if K is bigger than the size of the small set plus the equal set, then we know the K smallest lies in this big set. So we recursively run fast select on the big set with this K scaled. So we set K equal to K minus the size of the small set and the size of the equal set, this part that we discarded. Finally, if neither of these two cases held, then we know that the K smallest lies in the equal set, and therefore we simply output P. Now these three cases are simply the same as we detailed before for the quick select algorithm. This completes the pseudocode for our algorithm. Now we can analyze its running time, assuming that this pivot P that we found is a good pivot, and then we'll go back and prove that this pivot P is guaranteed to be a good pivot. Now we're going to prove that this P that we chose is in fact a good pivot. Now let's assume this fact for now, and then let's look at the running time of this algorithm. Let's look at the running time step by step. The first step, breaking A into these n/5 groups. How long does that take? Well, that just takes one swipe through the array A. So that takes order n time. Now we have to sort each group. How long does it take to sort one of these groups? Well, it's only 5 elements. So even if we use a super slow algorithm, let's say 5 factorial, we write down every permutation of these 5 elements and choose the one which is sorted. That's going to take us 5 factorial time, which is still order 1. So it takes us order 1 time per group, and there's order n groups, so the total time for this step is order n. Now we're going to run this same algorithm recursively on this subset S, which is of size n/5. So how long does that take? That takes us T of n/5, since this subset is of size n/5. Now we partition A into these 3 subsets. That takes one swipe through the array A. That also takes order n time. And then finally we recurse on one of these smaller subproblems. How large are these subproblems? Well, since P is guaranteed to be a good pivot, we know that these subproblems are of size at most 3/4 n. So our running time satisfies the following recurrence. We have 3/4 n. We have n/5 for finding this median of this subset S. And then plus we have order n for several of these steps. The key is that 3/4 plus 1/5 is 0.95, which is strictly less than 1. So this recurrence solves to order n, and we have an order n time algorithm.